Our project is to provide a solution to measure and analyze certain shipping environment parameters. The outcome of this project should help collecting beneficial and accurate data to help make shipping environments more protective to packages. And Ahmed will tell you more about that.
First, I want to explain to you guys some characteristics about the shipping process. It has many stages, and the package goes through different hubs as it reaches its final destination. The package can, this process is like a significant amount of this process is automated, and like it combines some human employees interact with the package, and also like machinery as well as like vehicles and carriers. These conditions can have a significant impact on the package, as deformities as well as the actual package content might also experience some damage. The shipping environment hazards can be these are the most typical ones: vertical drops due to mishandling, like a worker just dropping the package; horizontal impacts due to like machinery or vehicle vibration, machinery vibration as well; temperature and humidity extremes, and orientation changes that can be because some package content might be sensitive to orientation. So basically the requirements for our project was to measure and record these parameters and later on analyze the data. Other potential uses for our project can be vehicle vibration, storage condition monitoring, transportation testing, elevator and escalator monitoring, aircraft turbulence, as well as crash and impact testing. For, the design considerations we had to look at when designing our device was the long shipment time, and looking from power consumption, looking at our power consumption limits as well as memory capacity, like where we stored the data. We also had to consider the package size. We had to optimize the package size to reduce costs as well as to protect the device, and at the same time allow it to capture the data accurately. We also had to think about how to sample the data to be able to analyze data later on in the process. I'm going to explain the top level.
This is the top level design of our device. You can see it captures the 5 parameters that Ahmed just talked about. It takes the user input, which helps it to sample and analyze data more related to the user preferences, and then stores this data into external storage. This is a functional breakdown of our device. You can see for orientation, vibration, and shock, we use an accelerometer. For temperature and humidity, we use a temperature and humidity sensor, and we use a microcontroller for sampling and analyzing the data. And for our interface, we use an open lock. And for our external storage, we use a micro SD card. And for the user input, we use an LCD and 4 buttons. This is the accelerometer we picked. It's 3-axis accelerometer. It allows us to capture this data in every possible direction, and it's a digital one. It has a configurable resolution and range, and we set the maximum resolution range to get the most out of it. By capturing acceleration, we can determine shocks by looking for spikes in acceleration, which is actually the typical definition of a shock. Vibration, also vibration, because vibration is kind of a periodical shock that just has frequency components. For orientation, we get the sign of the acceleration, which is in G's, and that's the orientation on an axis. This is the convention we use to sample our data. Like this is the side view. We have the x and y axes. X is right and left, top and bottom, or positive and negative. And for our top view, we just have top and bottom for z-axis. Our humidity and temperature sensor is also a digital one with 0.1 degrees Celsius precision, same 0.1 percentage humidity precision. It sends its data using bit banging and timed pulses, and use timer to interpret the time pulses. For external memory, we use a micro SD card because it's compact enough and it offers a lot of storage, and you can easily extract data from it. For our memory interface, we used OpenLog, which implements the file system and communication protocols necessary to communicate to a micro SD card, and this reduces the load from our microcontroller to make it to the most important stuff. And it communicates to the microcontroller using asynchronous UART. And this is a microcontroller we picked. We use its real-time clock for time stamping and implementing sampling rates. We use timers to measure exact times and provide required delays. And we use the synchronous serial interface for supply communication and asynchronous for the UART. This is our software flowchart. As soon as the device gets powered on, it initializes the hardware and then asks the user to set the time. Once the user has set the time, he can choose to start using the default configuration or set the configuration of each sensor individually. Once the user is done setting and presses start, the microcontroller applies configuration and then continuously samples acceleration and looks for shock orientation and vibration to be more than the set threshold. And timer interrupts can happen to sample either humidity and temperature according to the sampling rate set by the user. And finally, when the user presses the stop button, it goes back to the start and config menu.
So I'm gonna go over a quick explanation about the user interface that we have. We decided to go with the LCD 4x20 character, and we also have 4 buttons. So we decided to have 4 buttons, and in each one of them we have different functionality. We decided to have up and down to basically to browse and changing the value on the LCD screen. We have the select buttons, basically just choosing the option on the screen. And the last button we have is called stop buttons. Basically, when the user press that button, the LCD screen will be displayed again, and then the microcontroller will stop taking data from all the sensors. So before I begin, I want to tell all these boxes will be exactly how it look like on the LCD when the device is actually working. When the device just start power, the page about entering the day and time will allow the user to changing the time and day based on the military time. And when the user they finish changing day and time, they can go to the next screen. It's called start and configuration screen. So if the user they're not picking up, they want to just use the same default values, they can just select the start option, and the LCD basically we turn off, and then the microcontroller will start taking all the data from the sensor. But where the user they decide to go with configuration sensor, this screen on the left will be displayed with it will show all the sensors that we have for temperature, humidity, acceleration, orientation, and vibration. So decide if the user they want to go with option 1 and 2, which is temperature and humidity. The sampling rate, that screen will be displayed for 15 minutes to 2 hour increment of 15 minutes. But if the user they decide to go with option 3, which is acceleration orientation, this screen will be displayed, and then the user will be just choosing either changing the threshold for shocking from 2G to 16G and increment by 1G. Or maybe they can change the orientation threshold from 20 degree to 70 degree increment of 10 degree. And the last option they can choose is the vibration sensor. We have the frequency rate of 10 Hz to 70 Hz and increment of 10 Hz. So I'm gonna go to Neel with the power circuit and hardware. So I'm gonna talk about the power circuit and hardware. This is So this is a chart of our power calculations. Basically what I did is I took a power requirement for all different parts of our device and added it up, and our total power requirement comes out to be 75.15 milliamps. And I'll talk about the battery in a second. Our battery capacity is 8,000 milliamp hours. So our time allowed for the device comes out to be 4.4 days. We decided to go with Energizer E93 C-cell battery. The most important reason was because it's shippable, and another reason is its battery capacity, which is 8,000 milliamp hours, is good enough for our project. We decided to use 4 1.5 volts Energizer batteries. So in order to reduce the 6 volts to 3.3 volts that's required for our different parts of the device, we used a LM317T voltage regulator. Here's a diagram of our actual diagram of the LM317 voltage regulator along with the diagram on the actual device. And as you can see here, the power, which is the heat generated, comes out to be 2.7 watts, which is good because, and we got the lower value because the input and output voltage that we're applying is relatively low. The number is small, so the heat generator the number is not big. And here's a diagram of our hardware circuit. We got a power circuit on the top left with the LM317T voltage regulator, along with the 2 sensors right below it, and the open log over here, which logs the data, along with the LCD and the buttons. That is all connected to the MSP430F5438 microcontroller. And this is a demonstration of our working device. Not able to get the sound effect, but basically he just set the thresholds. Now they're going to tape the box and do a little prototyping testing.
When the SD card memory system went blue, that means it's recording data.
I sound like my
So now I'm entering the SD card. Plug it into the computer. And there's our data file.
Who's the data?
Yeah, wasn't that funny? So I'm going to explain the memory system and the logging results. So our memory system, we use OpenLog. Basically, OpenLog powers up whenever we power up our device. It creates a new text file on the micro SD card we have. We store it every time a threshold is reached for a sensor or a sampling rate has been passed by, a data point can store it into our text file. As you can see, we have a timestamp and date and relevant information. This is the example of different information about our sensors that is recorded onto our text file. This is from our main test. So for log importation, we use Excel because Excel is able to organize a lot of data really well. It has various functions, formulas, and graphs, so we can do a lot of different statistical analysis on it. And also, Excel macros help a lot because it records actions and repeats it. So it's helpful for us because we have a lot of repeated trials. So this is our main file that we got. Our most successful run is 20 hours using FedEx shipment. As you can see, it ran from around 7 o'clock on April 23rd to around 2 p.m. on the next day. So I plotted these graphs and we're trying to make some information out of it. Around here is when we turn it on and we ship it. We took it to the shipping center. And as you can see, around this time, temperature steadily decreases, but it seems to be at a steady pace. So we assume it's being placed in an environment for a while. And around this time, we assume the package was taken out because of the spike in temperature. And we use a sampling rate of 15 minutes to give listener enough data to actually come up with some quantitative results. Similarly, for relative humidity, we use a sampling rate of 15 minutes, and around here, we can assume that it's being stored somewhere because the humidity is relatively constant. And around here, it seems the package was taken outside or something because the relative humidity shot up, and it was a pretty rainy day on the 24th. So for Shah, we set using LCD, we set the threshold to be 2 Gs because we want to quantify the shipping environment and want to be able to make sense of it. As you can see, it recorded a lot of, we created a histogram for Shah. It recorded a lot of Shah from 2 to 3 Gs. And we assume this is because of automatic handling and sorting equipment. And we only got rare instances where it might be actual drops, which is around here, which would be high amounts of G. The highest recorded shock we got was around 10.1 Gs at around, let's see, 8 p.m. They just threw it in there or something. And so I want to create quantify shock even more by doing a cumulative percentage versus shock. As you can see, to read this graph, you have 5 Gs over here, and it's roughly about 99%. This means that 99% of the data we have is less than 5 Gs. So in a standard shipping environment, it's going to be, most of the shocks you're going to get is because of, they're just sorting it and placing it around. And few is actually going to be around with drops. And so we compare this data with what other people had previously in previous literature, and we got the same sort of graph, except they did drop height and we did shock. Here we try to graph vibration. We got a real-time vibration over here, and we have a power spectral density, which is, this is what we're comparing to, and this is what we use MATLAB to calculate. As you can see here, the frequency, we receive a lot of activity on the lower frequencies due to the tires and the suspension. And we have activity around the same lower frequencies, and we assume that this is the standard truck environment. And this is also real-time vibration on the z-axis. For orientation, we plotted in histograms, and we took a small sample of what happens in the journey, 2 or 3 hours into. And we graphed the orientation and separated it into x and y axes. And we found out that it spent most of the time 75 degrees to 90 degrees oriented to the left in the x-axis. And we graphed the z-axis here. 81% of the time it's right side up, and 19% of the time it's upside down.
I'm going to go over the problem we encountered as we tried to test our device by shipping it with different carriers. We used first our package design. We used a regular parcel box and glued wood on it, and we just screwed the battery holders and the vector board on the wood to make sure it's mounted properly inside the box. And the shipping trials we ran with two with USPS ground and priority, and one with FedEx. And it was in Maryland. The location was in Maryland, and we included a note that explains our project and contact information, other stuff like that, in case anyone had like any security concerns with the package. The package was actually opened on the first run with USPS, and the battery holders were taken out, and they left the battery holders in the box, so like when it continued the shipping, it kind of damaged some of the components on the board, and we were only able to get 1 hour and 47 minutes of data. The second run, we had to modify the package to like separate the batteries from the design in case it happens again. And they suggested that we use priority because like it's less likely to be inspected. Then we actually this is the modified package design. We see the battery holders here on the side. Still opened it, and they damaged the battery holders, and we got only 1 hour and 3 minutes of operation. And finally, our successful run with FedEx, and we got 20 hours of data. And these are samples from the first run with only 1 hour. Same thing, histograms for shocks and orientation, only 2 points for humidity. This is samples every 30 minutes, and 4 points for temperature, because the samples every 50 minutes.
This is the cost spent. The actual cost of our project is actually less than the amount we spent because we had some redundancy of components, and some components were not used. And this is the total shipping cost for the 3 times. This is the hours we spent, and the learned lessons. We basically learned that integration takes a lot of time, and we need to prepare more for it, and actually spend more time planning, and that will help a lot in reducing the debugging time, which is actually could be more. Just for future modification, we thought that we might need a higher version of another version of MSP, the same microcontroller with a higher clock frequency to be able to sample more. This is actually, we can only sample at 310 hertz per second, 310 hertz. And for vibration, we wanted to add like more continuous one, at least for 600. So we could upgrade the microcontroller to one with higher CPU clock.